Alright, now, all this is well and good. Being able to find the orbits of functions after iterating. We have the number line thing, we have a little function that we use to iterate to actually give us all this. But there is an issue. The problem is, when you want to actually see this, it's fine to be able to see it like this, but you saw how we had to play with it to actually figure out this. And there's also an issue that some behaviors of points are actually hidden in this number line way of showing things. Right? So instead of this, there's another way of visualizing this, and that is called graphical analysis. Right? It's called graphical analysis simply because it uses the graph of a function. The graph meaning an xy plot of the function, where x is the input and y is the value of the function, that corresponding points, corresponding x values. So you can use that to actually figure out the iteration, but it doesn't seem very straightforward, does it? I mean, think about it. If you had, let's just take graphical analysis of a function. If you had a function f of x, right, and you wanted to actually do this, you could plot this function on, say, let's say, something like this. So this is an example of a graph, right, of a function. It's not exactly square root would become a little more like that, but it's close enough. So suppose this was a square root of a function, and you had to actually plot this, you had to find out the orbit of a number on this function. Well, this is the plot for root x. Right? If I wanted to find, so this is f of x equal to square root of x. Right? Now that's well and good. The problem is, if I wanted to actually find what is f or twice, or f thrice, or f 4 times, right? I would have to actually redraw this graph for those functions. I would have to draw a graph for square root of x. Right? I would have to redraw it for another graph for square root of x. Right? And this means that if I had to find iteration, some of these things, they take a lot of time to actually converge at a point. So if I had to iterate 100 times, I would have to actually draw the graph of square root of 100 times x, which is really not practical. Right? So this kind of, it's possible in theory, but it's practically very hard since you can do it. However, there is another way of doing this, which actually allows us to find the behavior of the orbit of any point using the first degree graph. And that is what we're going to discuss right now. The method is very simple. I have an example over here, which is basically just to first draw a line passing through the origin with slope of 1, which means y equal to x. Right? It's a straight line. For any point of x, the corresponding value of y, and you just join them, and you get a straight line over here. This you first draw this line. Now let's see how we can actually use this thing to do what we have to. So consider this. We want to find, let's say, this point over here. Let's call it T. Alright. Just call this thing. So this would be, the x value would be T, and the y value would be 0. I'm talking about this point over here that my cursor is right now. And what I do is, if I want to find the corresponding value of the function, I go up. I go up till I hit the red line. That's over there. So this point would actually be, the x has remained the same, so it's a T. The y has changed to, let's take it from here. The y has changed to square root of T, because anything on this would, x of any value, the y value of at a point on this curve would be the square root of the x value of that point. So it's this point marked with a purple circle. Now what I do is I move leftwise or right, leftwards or rightwards, depending on where this line is. So I go here and I reach this blue point till I touch this line. What would be the value of this? Well, the value of this would be, the y does not change, but the x does. Right? And the thing about this point, this line, is that x and y will have the same value. So this point would actually be square root of t, comma, square root of t. Right? So this would be the square root of t, comma, square root of t. And I can actually, then from here I go up or down depending on where my original curve is, and till I hit that, and that's this green circle over here. So this would be what? The x has not changed, so the x is still square root of t. But now it's used because of the curve, it's the square root of that. So it actually be the square root of the square root of t. You get here. And from here we move left or right again, and we reach this. So this would be again the and we repeat this, like if I want to do this again, I'd come here. This would be square root of t, square root of t. I go down from there, I'd come here. That would be square root of that would be square root of t, and square root of square root of t. And go on like this. So the general technique is to start from somewhere. So we try to just to bin these out a little bit. Let's just dig these out, and then if I want, the way I do this is you'd start from here, you go up all the way here, then you'd come this way, then you go down here, then you go here, then you go here, then you go here, then you go here, go here, go here, and then you repeat it like this. This is the way you do it. You start from here, go like this, like this, like this, like this. So I will be able to actually find the orbit of this point t. It's these circles, the purple one here, the green one here, this one, etc. I'd find the orbit of t using just the first order curve. Right? This is graphical analysis, and it's extremely useful. It's a little tedious to do it on a graph directly, but we can always use a computer to do this for us. And then we can actually see the orbit of a function, how it behaves and things like that. And some mystery numbers which we saw earlier start to make sense. So we'll see that in the next segment.